So hey everyone, today we will be looking at the VHDL code or implementation of a 2-bit magnitude comparator in VHDL code. So let's jump right in. So first of all, you want to create a new project. Let's call this mag comp 2-bit. This is the project which we want to do it, and remember it should be in schematic. Click on next. Now oh, it already exists. Sorry, I've given some other name. 2-bit 1. Click on next, and let's say here we have to click VHDL because I'm implementing it in VHDL. So please check which language you're implementing the 2-bit magnitude comparator. Click on next, next, finish. So here I've created another they've created a project named MacComp 2-bit 1, and here right click on this and click on new source. So here give the name for this, give a new source name for this. So let's say we are giving it as test bench, and we are implementing test bench now, so we are giving the name as test bench. So click on VHDL module and click next, next, finish. So now we have created a new source module. So this is inbuilt, so you can remove this and also remove this. It's not necessary at all. So now we are going to implement test bench for a 2-bit magnitude comparator. So what is a test bench? Before we start doing this, a test bench is something which is going to define the functionality of something. So for a magnitude comparator, we can use a test bench to give the input, all possible input combinations to a magnitude comparator. That's why we are using a test bench, because it is going to contain the zeros and ones binary values which are given as inputs for the 2-bit magnitude comparator. It is basically used to verify the functionality of magnitude comparator. That's why we are using the test bench. So the first things which you want to do is you have to include a library called IEEE in this one. So I'm going to do this now. So library IEEE, and then you're gonna include a standard library called a standard package called std logic, and then specifically 1164.all. So basically you are including a standard package which is going to contain the logic types which are really important, like the standard logic type which is going to which contains the binary representation 0 and 1 within itself. So we have to include this standard logic 1164 which is present inside the IEEE library. Next line you're going to include uh, another IEEE package which is called numeric standard, and in this you can, and by including this numeric standard you can perform numeric computations like signed numbers or unsigned numbers, positive or negative, or even operations plus minus something. So this is why we use numeric standards, which is also present in IEEE library. And the next thing is you're gonna declare an entity called, since we are using a test bench, we are going to give it test bench comparator. So now what is this entity? So basically an entity is nothing but something which is used to describe an interface. Here our interface is VHDL and we want something to describe our VHDL, right? So it basically describes the interface or designs the interface of uh, yeah, it basically describes the interface, and then you're gonna end the test bench comparator. So what I have done is that you have created an entity and you have named it TB comparator VHDL, and here you have not included any ports within entity. Usually there will be ports, but for a test bench we are not going to include any external ports, and we have ended the TB comparator VHDL. So now what we are going to do is that we have to define the architecture of the uh, things which we are talking about. So architecture, we are going to name this behavior of the entity which we are talking about, comparator VHDL is, right? So we are going to declare the entity now, architecture now. So we are going to declare a component for the architecture, component declaration of comparator. So what is this? So we are going to name this component as comparator VHDL. So we have created a component named comparator VHDL. So up until now, architecture behavior of TB comparator is this. So basically this line marks the beginning of the behavior section which you are going to implement. This section describes the behavior or functionality of the test bench, what the test bench is actually going to do, the functionality of the test bench. And yeah, in the comment says it all. The comment says that we are going to declare a component in the next line. And component, what are components? So components define the interface of the VHDL which we are implementing. It Components are the ones which define the design unit present in a interface, which is the VHDL we are using. So complement, in the next line we have declared the complement with, and always remember that the components will have a specific inputs and specific output ports. Okay, so specific number of input and output ports. So in the next line what we are going to do is that we are going to declare the ports which are present in this component, and those are um, A, which is an input port. So we are going to declare a port named A, which is an input port, and it uses it, and it is also a 2-bit vector. Always remember that ports A and B, which B is another port which we are going to do. A and B are 2-bit vectors, and output ports are always 1-bit. 2-bit vectors are A and B, and the output which we will see as A less B, A grade B, and A equals B are all 1-bit. So that is why we are writing standard logic vector 1 down to 0, 1 down to 0, close it. Similarly, B is also an input port and is also an 2-bit vector. So standard logic vector 1 down to 0, close it. And now we are going to define the output ports which are A less B output port, and since this is just one bit, we don't have to include vector in this. Standard logic, only this is enough. Similarly, A equal B out standard logic. This is also one bit. Similarly, A greater B out std logic. So we have declared two input ports and three output ports. So I'm going to close it here. I'm going to close it here, and then I'm going to end the component here. So we have, in an architecture there are two things, remember, ports and signals. We have defined the ports, but now we have to define the signals. So that's why we are going to implement the input and the output signals. So I'm going to define the input signals, which is going to be A and B. Signal A, I'm going to define it as std logic vector. Remember, this is a vector. A and B are always 2-bit vectors. No matter if it is a port or signal, they are always 2-bit vectors. So implement standard logic vector 1 down to 0, and then initialize the signals to 0. Similarly, do this for B2. Signal B standard logic vector 1 down to 0, others So what I've done here is I've initialized signals A and B, the values to zeros in A and B signals. These are all input signals and 2-bit vector input signals. So the next thing I have to declare the output signals, which is A less B, A equal B, A greater B, the outputs. In this, what I'm going to do is I'm going to implement signal A less B as simply std logic. There's nothing implemented here to be implemented here because it is already only one bit. So signal a a a equals, right, equal b std logic signal a greater b as std logic So what I've done here, I've implemented three signals here: A less B, A equal B, and A greater B. These are all output signals, and they are only 1-bit signals. So in the architecture, I have two things: ports and signals. I have defined both of them. So now we are done with the architecture. Now we are going to move into the main body of the um, test bench. Alright, so we are going to start with begin, and now we are going to instantiate or create the comparator. We are going to create the comparator in VHDL. So how do you do this? So basically what you have to do is you have to map the port A and the port and the input signal A. Similarly, port B with input signal B. A less B to output signal A less B. Output port A equal B to output signal A equal B. So that's what I'm going to do now. So before that, you have to give a name to this comparator, right? You are going to create. So I'm just going to give it as UUT, which is just a label to denote or to name. You're just giving a name to the comparator. UUT comparator VHDL. We are implementing the comparator VHDL, and you are going to map the ports with the signals, right? So you have to use port map here. So what we mean by this is that we are creating a name for the comparator we are going to create, and we are going to map the ports and the signals together. So that is what we are doing here. And then, yeah, as I said, you have to map A with A output to input port A to input signal A, and similarly with B and A less B with A less A less B and A equal B with A equal B and A greater B with A greater B. Yeah, so now we have declared the output port map. We have mapped it correctly. So now we have to close the yeah. Now you have to generate the input values, right? So that's why you are going to create so the stimulus. What is a stimulus? It is the input values, generation of input values. You are going to do it here in this process, stimulus process. And what you're going to do is you have to name the process, right? So you're going to name it as stim proc is you're going to name this process as stimulus process, stim proc, and then you're going to begin the process. And then what you're going to do is basically what you're doing in this is you're creating test cases for all possible 2-bit combinations, right? Yeah, 2-bit combinations. So now you're going to implement a for loop which is used for iterating from in the 2 bits, that's from 0 to 3. So for I in 0 to 3 loop, all right, end loop, all right, and you have to use another nested loop in this for j in for j in 0 to 3 loop and end loop, all right. And inside this, what you're gonna do is that you're gonna so we have an integer variable I and j, so we have to convert it into a 2-bit vector. We are going to convert I, integer variable I, into a 2-bit vector a, and we are going to convert integer j into 2-bit vector b. So for that, what you have to do is standard logic vector 2 unsigned I comma 2. Similarly, you have to follow the process for b2. B standard logic vector 2 unsigned j comma 2, and then now we have mapped I to 2-bit vector a and j to 2-bit vector b. Now you can introduce some time delay. This is just basically for our convenience. We have to view the waveforms correctly, right? So that's why we are doing this. So wait for, let's say, 30 nanoseconds, and yeah, so we have end the loop and you're gonna wait, because the reason why we are including wait here is because we don't want to continuously keep on generating the test cases, right? Once we get all the test cases once, we don't have to generate it again. That's why we are stopping it, or wait, we're just implementing wait here. So, and then after this, end process. So I'm just going to check if it's in the same line. It is. So end process, and then finally end. So this is the test bench code for the magnitude comparator, 2-bit magnitude comparator. So let's check the alright. I've done some minor corrections like giving spaces, etc. So let's run it again. Yeah, so it is done. So now click on simulation and click on this, and you will be able to see behavioral check syntax. You'll click on this and verify it. Yes, it is correct. So this is the test bench output which we want. So everything is perfect till now. So now we are going to be implementing the actual 2-bit magnitude comparator code on this test bench code. Alright, so for that you're going to click on this and click on right click and click new source. Okay, now you can add actual, because this is the actual code we are going to implement. Actual code and VHDL module, and click on next. Next, finish. And then what you're going to do is that you're going to remove all this. It's not necessary. It's not necessary. So now you're going to be implementing the main actual VHDL code for actual VHDL code for 2-bit magnitude comparator. Actual VHDL code for 2-bit magnitude comparator. Now same things, you're gonna do the same things here. So include library IEEE, and then you're gonna include use std logic 1164.all. Sorry, this is in IEEE, right? So IEEE dot. So next what you're going to do is you're going to create an entity named comparator VHDL. There it was TB comparator VHDL, but here it is entity comparator VHDL, and you're going to declare some ports for this one, and those are this. So here the input ports are A and B, and we are gonna implement it as together. A comma B is in std logic vector. This is a 2-bit vector, if you remember what I had told. 1 down to 0 equal to, we don't have to initialize it right now. So two inputs, we are just defining the inputs, that's it. Don't have to initialize it with 0. So A less B, here it is out std. This is a 1-bit, right? This is 1-bit, so we don't have to include vector. So here A equal B out std logic A greater B out std logic. So I've got A less B, A equal B, A greater B, and now I can enclose this with parenthesis, and we can end the entity in comparator VHDL right now. So yeah, now we have to look at the architecture of our main comparator VHDL architecture. We are going to name it as architecture comparator structural. There we use behavioral, we are using comparator structural of the entity comparator VHDL. Is we have to define temporary signals here. The reason why we are implementing temporary signals here is because we want to store the values. Alright, we want to store, so basically magnitude comparator is a combinational circuit. So we want to store the intermediate values which are shown as output in magnitude comparator. That's why we are using temporary signals to store the values. Since it is a combinational circuit, it is not a sequential circuit, we are creating new variables and storing the intermediate values in these signals. So I'm going to be giving it as signal tmp1, and we are going to be declaring 8 signals actually. 3 for A less B, 3 for A grade B, and 2 for A equals B. TMP5, TMP6, TMP7, and TMP8. All these are temporary signals. So now we are going to begin the architecture. Now for A less B combinational circuit, for A less B we have these. So the first variable we are going to assign it as not A of 0 and B of 1, right? Sorry, no, it's not the one. Not A of 0 and not A of 1 and B of 0. Yeah, this is I think correct. I think I'll check it again. Temp2 is not A of 1 and B of 1. Is it Yeah, I think this is the one. Yeah, and TMP3 is um, I think not A of 0 and B of 1 and B of 0. Yeah, so these are the three temporary variables assigned. These are logic implementations of the in order. First we are implementing A0 of A0, and then we are implementing not of A of 0, and then we are performing AND operations with not of A of 1, and then we are performing the final with B of 0. So basically we are performing not operation and AND operations in these A less than B to assign variables to temp 1, temp 2, temp 3. So next one is A greater than B. Let's say, so we have temp 4, we are going to assign it as, so we are going to assign it as not similar. Both A less than B and A greater than B are going to be similar, so I will copy this. You just have to change A to B and B to A. Similarly, you can also copy this too. Control V and change it correctly. Temp 5, temp 6, B, B, A, A, A. So yeah, the next thing is for A equal to B, and we are going to implement temp 7 and 8 for that. Only two things. Temp 7 equal to A of 1 x nor, here we are implementing x nor b of 1. Similarly, the last 8 one, we are implementing it as A of 0 x nor b of 0, and we are finally we are going to perform OR operation on this uh, A greater than B. Did here itself A greater B, we are going to be implementing it as temp 6 or temp 7 or temp 8. Alright, so after this you are going to end comparator structural so I will check. So yeah, I've got the correct things right now, so I will check the thing, and behavioral syntax check also is done. So we will check for the behavioral simulate the behavioral model here, and yeah, we got the output for the magnitude comparator. You can zoom out. So yeah, we got the output. So yeah, this is the output for the magnitude comparator. Sorry it took a little bit time for the output to come. So hope you guys enjoyed. Thank you.